Hi everyone. Today's topic is lazy evaluation. Lazy. What does that mean in the programming languages course? Lazy. Is it a good thing or not? We think that laziness is a virtue of programmers because programmers do not want to do the work that programs can do. So laziness could be a good thing. Let's see. Scala versus algebra. In Scala, we have a specific order for evaluating some expressions. When we evaluate some expressions, there is a specific order, 순서가 있어요. Meaning that when we have addition of two sub-expressions, we evaluate the left-hand side first in Scala, right? And then we evaluate parenthesized thing first. And then the remaining execution. In algebra, in the other way, order does not matter. When we have, addition of two sub-expression, it doesn't matter whether we evaluate the first sub-expression first or second sub-expression first. It does not matter. That's mathematics. That's algebra. In algebraic shortcuts, in algebra, if we see some, two functions, f takes two parameters, but it ignores the second parameter and just return the first parameter as it is, and g is another function that's really complex. Okay, then when we have this function call in mathematics, meaning f is being called with two arguments, and the second argument is really, really complex, but we know the definition of f, where the second argument is always ignored. Then we can go straight to 17, because the result of all the g calls, these many complex computation, will not be used. We know that in mathematics. Right? Then we'd like to take advantage of that knowledge. In lazy evaluation, we can do that. Languages like Scala, Java, and C, most languages that you are familiar with, I think, they are eager, diligent. They are called eager. 무지하게 부지런한 언어들이에요. An expression is evaluated when it is encountered. In these languages, Scala, Java, C, JavaScript, whatever you call that, in many languages, they are mostly eager in the sense that when you encounter an expression, it just evaluates it right away. Instead, languages that are being smart or being lazy, they avoid unnecessary work, and those languages are called lazy or being smart or clever. An expression is evaluated only if its result is needed. Okay? Yeah. Based on this definition, eager languages evaluate things as it is encountered. In lazy language, it evaluates only that's necessary. Yeah, only that's necessary. Sounds really charming, right? So we'll see how they are different. In the past, there have been multiple programming languages to be lazy, but most of them died. And the only modern, actually actively used lazy language is called Haskell. Haskell is really cool, and many programmers really like to learn Haskell, but it's not that easy. It's not that difficult, but it's not that easy. And because Haskell is kind of the de facto lazy language, and it's really close to mathematics, some companies and IT companies, they value Haskell programmers really high. When you look for your job as a programmer, then if you know Haskell, if you say, I am a Haskell programmer, then people will say, oh, you must be smart. So that's another way to grow your skill set. to include some cool languages in your skill set, like Haskell, Rust, or things like that. Just C or JavaScript, everyone knows that. But Haskell, Rust, or Objective-Camel, those languages are really hot. And when you say you are those languages programmers, then people will think you are a good programmer. Okay. LFAE is the name of the language that we are going to learn today. It's FAE with laziness. It's lazy FAE, in short, LFAE. Look at the concrete syntax. It has a number, addition and subtraction as usual. It has an identifier, function expression, and function call as usual in FAE. Wow! Look at that. Those language constructs are all in black, meaning there are no new language constructs. How come? Because FAE and LFAE, they have the same syntax, but different semantics. Wow. Which means that when we write those two expressions, unless I say which language it is, you don't know its semantics. Wow. When you read this expression, when you evaluate this expression, when you evaluate those in the FAE semantics, you are going to have something. When you evaluate that in the semantics of LFAE, you may have a different result. In FAE, let's see. What are they? They are function calls, right? This is one sub-expression. This is another sub-expression. And then what? This is a function expression. When you evaluate a function expression, you're going to get a closure V. When you evaluate this expression, what is that? It's an addition. It's an addition of number and a function expression, closure V. Num V and closure V, when you add them, what do you get in FAE? What do you get? Yeah, an error. It's not 3. The frequently made mistake is 1 plus 2 is 3. No way, right? We cannot add a number and a closure V. But that's the semantics of FAE. What about the semantics of LFAE? In this function expression, we do not use the parameter. In this function expression, we use the parameter here. Yeah? So, in this expression in LFAE, the value of x is not being used. In this function call, the value of x is being used. So, in LFAE, wow, the result of this one is going to be 0 because we do not use the parameters, we do not use the argument expression, so we are not going to evaluate it. So it's going to be 0. Here, because we need the value of this x here, what's the value of this expression? Again, addition of the number and the closure V, error. Wow, so that different. Even though we have the same syntax for FAE and LFAE. They have the same concrete syntax like that, but they have different semantics. In FAE, both are going to be errors, right? In LFAE, only this one is an error. But see, I said question mark because depending on how lazy it is, this could be an error or not. We are going to talk about that at the end of today's lecture. So you should stay tuned. Okay, implementing LFAE. How can you evaluate that? How can you evaluate this lazy semantics? We are going to explicitly delay interpretation of argument expressions. Delay meaning we are not going to be eager. We are going to be lazy in the sense that we are not, when we have function call, we need to evaluate function part. We need to evaluate the first sub-expression. We need to evaluate it and get the value and see whether it's closure V or not and evaluate the function body. But we are not going to evaluate the argument expression because we may not use it. right? We don't want to be diligent. Then what can we do? We are gonna freeze. We are gonna freeze this argument expression. Instead of evaluating this sequence of expression, we are going to freeze it and capture that in a new kind of value. Yes, in LFAE, we are gonna have yet another value. Remember, in FAE, we had two kinds of values. What were they? Num-V and clo-V. And in LFAE, we are gonna have one more kind, X per V. X per V. X per V captures an expression and an environment. Okay? We are gonna extend this value. We are gonna extend this value with X per V, which has two fields. One for expression, that's the argument expression, and what? The second for the environment. Why do we need to capture the environment as well? Not only the expression. What do you think? We are going to see that in a minute, but I will give you a hint. We are going to capture this expression at this point, and when we evaluate the function body, we may have a different environment. But we need to know the value of this argument expression at this point. That's why we are going to capture the environment. If you don't see that, don't worry, we are going to come back. Before moving on to actual semantics of this lazy evaluation, let's emphasize what we mean by laziness. Laziness, again, is a different semantics. When we have FAE and LFAE, even though they have the same concrete syntax, they have different semantics. Whether we have laziness or not in the language, the result of function call is gonna be different, right? But do you remember this EMV, the sigma thingy, right? What was that? It was a finite mapping from names to values. Why did we use this EMV? Instead of when we have, say, some expression that use identifier x in it, and when we know that x's value is 8, instead of replacing the value of every occurrence of x with the actual value 8, we remember that in this environment and then look up the environment when we need to use the value of x. So it's kind of deferring the evaluation of identifier, but it's not really deferring the evaluation. It's what? Deferring the replacement of the identifier with its value, just to look up the environment when we need it. And whether we are going to use this kind of implementation or not is a different algorithm, but the same semantics. Meaning that we can implement FAE without using the environment, but a different style. But that's just a different algorithm. Like when you implement a sorting algorithm, you can use bubble sort or merge sort or quick sort, different kinds of algorithms. But their behaviors are just the same. In laziness, it's not only different algorithms, but also different languages. One more time. When you implement FAE, whether we use EMV or not, it's just a matter of implementation detail, not different semantics. But whether we have laziness or not, that's different languages. Because it's important, let me repeat this in Korean and move on. environment를 사용해서 구현을 하는지 마는지는 구현 디테일이에요. 이거는 언어의 시멘틱스가 달라지는 게 아니라 똑같은 시멘틱스를 구현하는데 어떤 자료 구조를 쓸래? 어떤 알고리즘을 쓸래? 뭐 이런 거야. 그래서 똑같은 거예요. 근데 레이지니스가 있냐 없냐는 다른 언어예요. 똑같은 컨크리트 신텍스여도 FAE냐 LFAE냐는 레이지니스가 그 언어에 있냐 없냐는 시멘틱스가 달라요. 아주 다른 언어예요. Similarly, let's see. Have you ever heard of short circuiting? It's these operators, logical operators, and or logical and or logical or. In mathematics, if you remember that 정석 were your math in high school years, then we have truth table, right? 진리표가 있었죠? Truth table, meaning that and if one of those is false, it's going to be false. All the Oh, sorry. If one of E1 or E2 is false, it's going to be false. It's true only when both are true. And with this logical or, if one of that is true, it's going to be true. It's going to be false only when both of them are false, right? So as soon as we know one is false, we do not even need to evaluate E2 in mathematics. In this logical or, as soon as E1 is true, we do not need to evaluate E2 in mathematics because they are pure. In real programming languages, because they may not be pure, right? There may be side effects like mutation, exceptions, and things like that. So evaluating E2 may result in different results, even though E1's value is false in this and E1's value is true in this logical or. But in many languages, they provide this short-circuiting semantics, meaning that, in logical AND, if E1's value is false, it does not evaluate E2. In logical OR, if E1's value is true, then it does not evaluate E2. Again, it's a different semantics. Whether you have a short-circuiting or not, it's a different semantics, depending on the language. Just like laziness. And short-circuiting is not being lazy. Laziness meaning when we defer the evaluation of an expression when that's needed. But short-circuiting meaning just this logical AND and logical OR, and the languages have these kind of optimizations. It's optimization with different semantics. So that's a bit weird. That may not be a good property provided by C, but that's the semantics of C. Okay, then before moving into the actual implementation, we're going to see this running example. LFAE, it's a function call with this function expression and argument 10. How do we evaluate this? Let's see this implementation code that we made before. Let's evaluate the first sub-expression and call its value fv. And the second sub-expression, as we discussed before, we are not going to interpret that. We are going to capture that argument expression with the current environment in this new kind of value called x per v. If the value of f is not closure v, it's an error. If it's closure v, then we are going to have parameter body and the environment when the function is being defined. And as usual, we are going to evaluate the function body using this environment when that closure v was constructed. On top of that, we are going to use this value, meaning parameter's value is what? X per v. This time it's not actually value, but the expression hopefully be evaluated later. Then, when we have that, what's going to be f of v and what's going to be av? Yeah. F of v is going to be closure of v with the parameter name x. Body is going to be 1 plus x and environment is going to be empty. Av is what? X per v with this expression. It's not num v, but num and the captured environment. Then, what's going to be this new environment? What's going to be this new environment? It's going to be on top of the empty environment, parameter's value is this AV, right? On top of the empty environment, parameter's value is x per v. So far, so good, right? Then, parameter's value is x per v, and we are going to evaluate this body expression. Okay, then how do we evaluate the body expression? We need an addition. How do we evaluate addition? Oh, well, we evaluate the first sub-expression and the second sub-expression, right? Yeah. Then, what do we get? What do we get? Error. Why? When we evaluate the first sub-expression, we are going to have non-V. When we evaluate the second sub-expression, what? That's ID. What do we do with the ID? Look up the environment. What do we have in the environment? X per V. How do we add non-V and X per V? Error. We don't know how to add non-V and X per V. We are going to learn that after the first break.